Hello and welcome to the Oxford MAT Livestream. My name's James and this week I'm joined by Daisy.
Hi, I'm Daisy.
We're going to do some computer science problems today. My computer is making a very strange whirring noise, so for a couple of minutes at the start, we're going to check if the tech's working, check if the stream is actually happening, and make sure that stuff's go like that. It might be that I need to close some things, so we're going to try and work that out. Okay, Daisy, you're a computer science student, right? Is that
Yeah, I'm
at
a second
Oxford?
year. Yeah, at Somerville
Okay,
College. Yeah,
which means at some point a while ago you did the maths, right?
yeah, I did it. Well, it's nearly 3 years ago now when
Oh,
I
right.
went because I used to watch these streams. I think that's when they first started
Oh yeah, it was
in
about that sort of time.
2020.
Yeah,
Yeah,
pandemic times. And you've been
yeah,
on the stream before, right?
yeah. I was on the stream in last October. Yeah,
Yeah, that's it. We did a that was another computer science special.
yes.
Good times.
And in
Right.
fact, I was on two streams because the first one didn't work.
One person in chat says stream is blurry, but somebody else says, "Whoa, special guest." So you know. So I think we're live. I think I've managed to press the right buttons so that we're live on the internet. Look, someone says hi Daisy in chat, so they in some sense know that you're here. So that's pretty good. This is the computer science I expect as someone. Not creating websites with HTML or using Photoshop. We're doing solving logic puzzles today. All of the puzzles
Yes.
today are from the kind of logic puzzle era of time when that was what the question six looks like, which we did for a bit. Cool. I'm going to put a poll on for how was your day in chat because I always do that at the start. Sometimes I forget, so bit of a lie there. And I'm going to find out how their day was. Can you also let me know in the Q&A if you voted in the poll? Can you let me in the Q&A? Is the stream blurry for you? Is the sound bad? I'm lagging at 2 frames per second. Okay, I'm going to try closing some stuff. What am I going to do? I'm going to turn off chat on the stream. Sorry, chat. Bump. It's a nice feature, but it's a nice feature, but it's using CPU. I'm lagging. Okay, right. We're going to try and reduce lag. What else can I close? Yeah, some people are saying it's lagging. Too much MATLAB and emails. Not blurry. Okay, cool. Okay, and the voting is continuing. We're going to do the voting. And someone has just put the number 4 in chat as well. Okay. So Jay asks a good question, which is why have I put loads of logic questions on this sheet if there's not so many logic questions in recent years? And I've got my reasons. Daisy, do you want to guess why I'm getting people to do logic questions?
Well, they do seem relevant. It's the same kind of skill set that you might need in in maths and computer science. It's not complete. It's not. I think it's a good kind of introduction to the kind of later questions you might get in interviews or things maybe the sort of things you might want to do on the course. Like that there are you do have like at least I know in computer science you have to do logic like this on the course.
Yeah. So I also thought that this would be good for people, even if you're not doing computer science, and even if you're looking at other past math papers where there aren't logic questions, you might want to see some questions like this. Right, cool. Daisy, can you talk a little bit about what you remember maths being like? What it was like when you sort of did maths for the first time? I'm going to fiddle with the stream settings to try and make things less stop motion. So I'm going to go quiet for a second, and Daisy's going to talk
Yeah.
about maths from a computer science point of view. Thank you, Daisy. Go.
Yeah, so I remember when I first tried a past math paper and I got and I tried to do I didn't start right at the I started in the middle. I think it was 2012 I did, and I tried to do it timed, and then I looked through all the questions, and afterwards, and it was like I was just too embarrassed to mark it properly because almost all of them were wrong. But I kept at it, and I started going through them as I started to just do the map papers and mark them as I went along, and I started going along to the streams, and then eventually I did a few as a later papers time, because the later papers I think are a bit harder for the end ones, especially in computer science, like these question 6 and question 7. I was very good at these, but the ones in the later papers are a bit more difficult. And then on the actual day, I felt the mat went pretty terribly, but I got an interview, so that was good enough. But I think I did feel a lot of pressure when I sat the mat on the day.
I'm sorry, it's a sort of pressure environment to try and do math questions under time pressure, and in some sense that's a bit artificial, really. Like being in a test situation is always going to be weird, and real life is not a test setting, and I'm aware of that as someone who's done studying math questions and also had to face actual research questions in the real world, and they're nothing like each other. Doing the maths is nothing like being a sort of working mathematician. Less of a time limit for one thing. Cool. Okay. I think we should probably talk about some maths. I'm getting all sorts of error messages, so that's fun. My general default here is I don't know if we're live or not. How did the poll go? Was the poll all right? Oh, the poll came back as 4.1 stars in the chat for people to keep track of these things week to week. 4 stars with the majority voting for 4. Well, not quite a majority, but something like that. Okay, and chat's still going. I can see chat. My computer's calmed down a little bit, and I've got question 6 on screen. There's a question in chat that I want to send to Daisy, and then we're going to talk about this truth and lie question, which I'm going to line up like this. There we go. The question that I want to read out from chat is, what are the advantages and disadvantages of choosing computer science at Oxford over maths at Oxford? So I guess there's a choice that on some level you made, right? And I made a similar choice.
Yeah. So I guess an advantage is with, well, I think the main kind of difference is with computer science. It's the maths is generally much more applied. There is sort of some proof in computer science. There are a couple of like very pure modules that apparently are very much like the maths ones. Like we share like one module, I think, and that increases in the later years. But if you want to continue the sort of maths that you might do in the MAT, then actually I think computer science might have maybe a bit more of that, because it's less, at least from my perspective, it seemed less of really, really pure proof that you don't really get at A level or GCSE. And of course, the disadvantage of computer science is you have to do very applied topics. And I think the disadvantage of computer science over maths and computer science is that you have to do some like hardware topics, and you have to do things like compilers, which I didn't really enjoy. But I guess it's more about your preferences. I do get the impression that computer science is a bit less work than maths as a degree, but people might disagree with that.
I think you can go either way. So I will respond to Nav's point in chat. Nav in chat thinks that I had no choice with my maths degree, that I had to be a research mathematician at the end of it. That's not true at all. I could definitely be doing a useful job out there somewhere, doing something. Not that my current job's not useful, of course. Maybe Nav would prefer it if I was out there doing something else. Who knows? So I had to choose. I chose maths instead of computer science. I suppose for me it was more that I just can't do the kind of algorithmic stuff, the way of thinking of deciding between different plausible solutions, which one's more efficient or which one's better. I couldn't get my head around that at all. Um, so I think somewhere in between, there's this kind of idea that studying a bit of, if you're interested in stuff that's in maths and computer science, then you might be able to find some joint honours degrees out there. I know Oxford does a joint honours degree where you do a bit of both, and you've referred to the idea that there's both maths and computer science have to learn this sort of continuous maths or multivariable calculus kind of thing.
Yeah.
We both learn some of the same topics. In Oxford, at least, they're taught in a sort of similar kind of ethos. I always like to say that the very first computer scientists didn't know that they were computer scientists. They thought they were mathematicians, and in a lot of ways they were. Right, should we do a math question? I think we should probably do a math question. At some point. Chat ready? Chat. Miles wants to know why they're called Alice, Bob, and Charlie. I think it's a sort of cryptography thing, isn't it? Have you seen this, Daisy?
Yeah. Oh yeah, like you see this like Alice and Bob like all over computer science work, like problem sheets and lectures and exams. They were like all different topics. You'll find them.
We've got
like not just cryptography these days. It can be whenever the lecturer or whoever's teaching it thinks it's good to explain an algorithm.
Yeah, they would start ABC, and they're a little bit, I don't know, a little bit old school in a way. I don't know how many people are called Bob these days, but I don't know. Sorry if you're watching and you're called Bob. Your name's not inherently old school. Have you considered Robbie though? Just saying. Okay, right. I've done enough throwing shade at people based on their first names, which is probably going to get me cancelled. So I'm going to stop talking, and I'm going to let Daisy talk about this truth or lie question. Would you like to start by reading out the question? I've no idea how high definition the screen is. Someone said it was blurry, so I'm worried. So if you read out the question, I'll do the sort of cameraman thing of moving around.
So Alice, Bob, Charlie, and Diane are playing together when one of them breaks a precious vase. They all know who broke the vase. When questioned, they make the following statements. So Alice says it was Bob. Bob says it was Diane. Charlie says it was not me. And then Diane says what Bob says is wrong. And then each statement is either true or false out of those four. And then we've got 6 parts of asking about if these people are lying and telling the truth, and who did it, basically. Yeah. So, do you want me to read out the first part?
Yeah, I guess we're going to go through them in order. I'm not sure. Yeah. Sometimes I like to think about the question before I've even read any parts of the question. I like to think about whether I've understood it. But I think this one makes more sense if we sort of get going, right?
Yeah.
So yeah. Let's read part 1 out. Someone in chat says their screen is good.
Yeah. So the first part is to explain why at least one of the 4 must be lying. So I think here what you'd want to do is look. Okay, assume all of them are telling the truth. Can we see a contradiction there? And I think straight away, if we look, if we've got Alice and Bob both telling the truth, then that means that 2 people have broken the vase. But we know that only one person broke the vase, so we've got a bit of a contradiction. And I think there's also another contradiction here, because Diane says that what Bob says is wrong. So if Diane is telling the truth, then Bob can't be telling the truth. So at least one person is lying. And so the next part is to explain why at least one of them must be telling the truth. So I guess we could use the same idea here. So we could say if Bob, so if Bob is lying, then Diane is telling the truth, which is a contradiction. Whereas also if
Yeah, so B and D directly contradict each other.
Yeah.
So if B's lying, B's telling the truth.
Yeah. And then if Charlie's lying, then it was Charlie. But then that means that what Bob said was wrong. So Diane is telling the truth as well.
Right. Cool. Okay, so you're following through this kind of chain to say, well, suppose all four of them are lying, and then chasing through a kind of contradiction. And I was on mute because I've got loads of background noise today because everything's linked together. The stream is laggy, therefore my PC is loud, therefore my microphone is bad. So I'm just trying not to be here while also making it run. So I'm just gonna nod. I'm just gonna mostly nod. So C lies. Sorry, I was writing it out on the screen as well. If C's lying, then it really was Charlie. They've denied it, but if everyone's lying, then in particular Charlie is lying to defend themselves. So it was Charlie.
Yeah.
And then in the midst of that, in this world where everyone's lying, this kind of hypothetical world where everyone's lying, Diane has thrown this really weird shot at Diane's throwing this really weird shot at Bob. Because so Diane's kind of, if it was Charlie, then we've caught Diane telling the truth. So it's kind of opposite world. If they're all lying, then Bob and Diane is a really weird pair, isn't it? Because if they're all lying, then Bob's lying. No, it wasn't Diane. Diane's lying, and that's kind of an admission in this all lying world. Good. Okay. Cool. Do you know the funny thing? So just the PC banter in chat as well, because people are telling you to get a new PC. I did get a new PC. I've got a supercomputer that I built. It's amazing. I'm really proud of myself as well because I'm not a computer person, but I put together my own PC. It was absolutely brilliant, and for a few months the streams were just amazing. I was doing them from home in the pandemic, and for a few months the streams were just fantastic. And then I developed incredibly bad internet problems from home that meant I had to move the whole setup into the office. So we've been doing the streams from the office, and I haven't brought in the supercomputer. So until I bring in my home PC into work, that is the problem. And I will try and post specs in chat, and that'll be my thing to do. Right, cool. Sorry, Daisy, I've interrupted terribly to bang on about build a PC. I'm going to shut up again, and you'll be pleased to know I mute myself so that you can't hear my PC either, and let you do part 3.
Okay, so let us suppose that exactly one of the 4 is lying, so the other 3 are telling the truth. So who is lying? Who broke the bars? Explain your answer. So I guess here we could just try we could see what happens if every single person's lying, and then see if we get contradiction or not. So if Alice is lying, then if Alice is lying, then we know it wasn't Bob. So then Bob, Charlie, and Diane must all be telling the truth. But then that's a contradiction because, as we know from the previous part, Bob and Diane can't both be telling the truth. So we know that Alice isn't the one lying. So if Bob is lying, then Alice, Charlie, and Diane must be telling the truth, in which case Alice says it was Bob, Charlie said it wasn't me, which is consistent, and then Diane says what Bob said is wrong, which is also true. So that seems consistent. So it seems like it was Bob that did it, and Bob's lying. Just to follow it through, if Charlie is lying, then Bob and Diane would both have to be telling the truth, wouldn't? Which, as we saw before, is another contradiction. And if Diane is the one lying, then Bob is telling the truth, but then also so is Alice, which is another contradiction. So the only one that's consistent is Bob is lying and Bob broke the vase.
I think part of the challenge of doing this out loud is that you're sort of constructing a kind of truth table, right? I can sort of almost see it in your eyes.
Yeah.
This way of working through. Jay, ages ago, Jay in chat said, this question is kind of like, you make a truth table and then you're good. Do people in chat know about truth tables?
I didn't when I sat the mat. I remember that.
Yeah, maybe we should teach that. Should we teach a thing? We don't really do that on this stream. We could have a go. We'll have a go. So I guess we want a table. These are kind of all the possibilities, right? There's not very many. And which way around am I going to put this? I'm going to put the statements that we got from the people down this side, because that's the top to bottom on the page. So I want to do it this way around. Come on, PC, we can do this. Together, we can write the letters A to D. There we go. Okay, we've got their statements. And they've also got, like, separately, a kind of different dimension for the data table is who the criminal is. Is it a crime to break a vase? Depends whose vase it is, I suppose.
Yeah.
Where the vase is. Anyway, okay. Well, it could be Alice, Bob, Charlie, or Diane. And this is a good way to lay out the data, because now you can keep track with ticks and crosses whether their statements are true or false in each case. I'm going to get this wrong. Daisy, help. Shall we fill in the table?
Yeah.
Do you want to work column by column or work row by row? I think column by column, but I'm not sure what makes more sense.
Yeah, I think column by column would make sense. Yeah, I think that would be easier. But
yeah, okay, we'll go column by column then. So thinking about each of the potential criminals, consider the possibles.
So if Alice broke the vase, then it wasn't Bob, so that's wrong. If Alice broke the glass, then Bob's also lying, so that's wrong. If Alice broke the glass, then it wasn't Charlie, so that's correct. And also Diane's correct because And then if Bob broke the glass, then Alice is correct. Bob's lying. Charlie's correct, and Diane's telling the truth. If it was Charlie's, then Alice is lying. Bob is lying. Charlie's lying, and Diane is telling the truth. And then if it was Diane, then Alice is lying. Bob is telling the truth. Charlie is telling the truth, and Diane is lying.
I'm so sorry, I've realised halfway through that we should maybe have gone row by row to think about their statements, right? So you can read that column by column like we did to say each of the possible criminals, or if you could read it row by row and say Alice's statement is true if and only if it was Bob.
I agreed with what you were saying, so I'm to blame, really. I should have done better. But I think this makes the question a lot easier now. Anyway.
Yeah, so I guess now you can read off. Someone in chat says, "Congratulations, you've just got 15 marks." Because now I guess you can read off the information for each of the parts, right?
Yeah.
At least one of the four is lying. Well, in each column there's at least one cross. At least one of them is telling the truth. Well, in each column there's at least one lie. Okay.
Yeah.
Exactly one of the four is lying. Hold on while I count the lies in each column. aha, it's just column B. Yeah, okay, so once you've laid out the possibilities, it helps you scan across so that in your head you're not thinking what Diane says in this particular case that I'm thinking about is all currently false because Bob was actually telling the once you've thought through every possibility, you can just look at the table rather than ever thinking again about Bob and Diane. And it gives you this nice way to visualise this kind of direct contradiction between all the cases with Bob and Diane. They disagree in every single case, which is slightly different from the way Alice and Bob are never telling the truth at the same time. So the kind of Alice-Bob comparison is helpful for part one. If you want to prove that at least one of them is lying, that's like finding a cross in every column, and you can do that just looking at A/B. They're never both telling the truth. But then the A and B comparison is kind of not helpful for part two, because they're just lying way too much.
Yeah.
For you to prove that there's always someone telling the truth. The kind of way that they disagree is different between A and B, B and D. Are there any other pairs like that? Oh, I haven't really thought about the way C comes into it, but I guess C's just... It's like a really wordy game of Minesweeper, says Anonymous.
Yeah.
And Cyril uses ones and zeros for truth tables, which I guess would have been on theme for the kind of computer science episode, so maybe I should have done that. Good shout, Cyril.
Normally we'd use zeros and ones, but
would you?
This is good enough though.
Oh, I've missed the chance to put some like nerdy matrix ones and zero binary stuff on the screen. That's a shame. I shouldn't have said matrix there. I'll make them think. Anyway, good. Ivo in chat's defending computer science GCSE, which got some thumbs ups for that. There you go. People are talking about A levels as well. Good. Okay. My YouTube viewer thinks that the stream has crashed, so I'm just going to keep going and see what happens. We were on part 3. You convinced me it was Bob, actually. I wrote maybe Bob on screen, but then you did convince me that that's the only case that makes sense. So I'm happy. Cool.
So,
yes. Okay. 4 then.
So let's just now suppose that. Let's now suppose that exactly one of the 4 is telling the truth, so that the other 3 are lying. Who's telling the truth? Who broke the vase? Explain your answer. So we could just look column by column. So if it was Alice, then there were 2 people telling the truth, so it's not Alice. If it were Bob, then there were 3 people telling the truth, so it's not Bob. If it were Charlie, then that's 1 person telling the truth, so it could be Charlie. And if it's Diane, then it's 2, so it's not Diane, because that's 2 people telling the truth. So the only person it could be, looking from this table, is Charlie. So Charlie. So Charlie broke the glass, and Diane is the only one telling the truth.
Sure, and that was a good illustration, I think, of once you've got the table, you can just sort of scan through the table without thinking about the statements again. You could have worked through there, going through all the cases for the statements to say, aha, consider which one of them is telling the truth. Try and check for consistency through the statements. And there's something quite fun in that, really, about chasing them through like a sort of detective character, thinking about all of the things. So, yeah, but the table really helps, doesn't it? In particular, this last part is going to be the other 2, right? We've had maybe Bob, we've had maybe Charlie. In fact, we checked it was Bob. In this case, Charlie in this case. This is the other case, right? We know that we know that at least one of them is telling the truth, and at least one of them is lying. So, how many are telling the truth? Is either 1 or 2 or 3. You can also see that in the table. There's either 2 or 3 or 1 or 2 of them telling the truth. Yeah. We've done which column's got 1 in, which column's got 3 ticks in. Now we're asked which column's got 2 ticks in. That's Alice or Daisy, right? Not Daisy. Sorry, you're
Diane.
You're definitely innocent. Oh my goodness.
It should have been Daisy.
Yeah. Oh, yeah. Sorry. Cool. Now my everything's side crashed. Good. Okay. And then there's this weird part at the end. Hence, show that if we don't know how many of the 4 statements are true, then any one of the 4 of them could have broken the vase. What would you say for this part? I'm interested.
So I guess what I would do here, I would look back at the work we've done. So if none of the statements are true, then like that's a contradiction. If all of them are true, that's also a contradiction. So we've just got to check if one of them is true, 2 of them are true, 3 of them. We've already done all the work for that, basically. So, and we know that we found circumstances where all of them could have broken the glass. Or the alternative way of doing it with the truth table is to just see that we're able to come up with a situation for all of them where they're the criminal. So it's any of them could have done it from the truth table.
Yeah. I don't know if this is quite true or rigorous, but if you don't know how many of the statements are true, then you don't know anything. It feels a bit like, to me, if you don't know how many of the statements are true, then what are we doing? You can't trust any of the information. You have no information. So it's going to be, it could be any of them, like it says at the top of the question. Now maybe I'm missing something about the way that propositional logic actually works when you get down to it. Maybe if their statements are really super weird, then maybe you can build something which...
Yeah. Because the only way I could see this, I could like immediately see that not working, is because, for example, like Diane's statement depends on Bob's statement, for instance. So it's somewhat of, but we can just, but in that case it's just a not Bob. So we can work around that. So I can't see any reason why.
Is it possible
it wouldn't work?
So I set this as an extension question without thinking about it too much. So if you downloaded the question sheet this morning or something, then you might have already had a look at the question sheet, people at home. There's an extension question, but I didn't really think about it very much. And I sort of want to reopen it, I think. So I'm worried that, this kind of, you could come up with some sort of weird logical thing where Diane says something like, it was Bob, unless I'm lying currently, or something. So that there's like a logical contradiction if it was Bob or something.
Yeah, because I think this is the thing where it's between where we're converting like natural language into like logical, into like a logical into just normal logic, like formal logic.
Yeah, which is really dangerous.
Yes.
False implies true is true, so anything is possible, says someone in chat. But yeah, I'm worried about, if their statements are really conditional and potentially not just accusatory to each other, but potentially illogical statements that...
Yeah.
But then if it's conditional and potentially contradictory, then you can just say that it's false, I think. I'm back to thinking it doesn't matter. Right, good. Okay. If you want a proper answer to the extension question, I'm afraid you're going to need to do some sort of logic and proof course.
Although there is quite an easy. There is one case it's quite easy, because I think you said if there were n suspects, but if there were only one suspect, so if n equals 1.
Oh god.
Then we can
Okay. If there are 0 suspects, then if there are 0 suspects, then I really don't know who broke the vase. I don't have any statements to go on, and yet somehow I'm also confused. Right, yep, cool. I should probably have... Yep. Told you, where's the extension gone? It's down here.
Yeah.
The instructions to overthink the last part. Cool, right, okay, there's a question here. We're not gonna do it anymore. Cool, okay. Should do some hats. Do you want to tell them roughly about the kind of tradition of hat problems? If you know about the tradition of hat problems, I suppose. This isn't the first and only question that's got hats in it.
There are a lot of. I think the older MAT papers had a lot of hats in them.
Okay. There's also
The new. I can't remember if any of the new ones did.
we haven't done hats in a while. This is
Yeah.
not a leak of MAT 2023. I'm not thinking about this year's test when I say this sort of thing. We haven't done a hat problem in a while. I think this is the only hat problem we've got on MAT questions. But I suppose I'm aware of other hats problems out there. Of sometimes the setup is like this, where people are sitting in a row. Sometimes the people are sitting in a circle. Yeah, there's logicians wearing hats, and you have to say if you know that you're wearing a blue hat, and somebody over there is going to ring a bell. And there's all these you have to leave the island if you work out that if you work out you're wearing a blue hat, you got to go. That's a sort of tradition of these logician puzzles where everybody's wearing a hat.
Yeah. Well, I think it's maybe more realistic than some of the other scenarios. Maybe.
Yeah,
I'm not sure.
this. I prefer this to the kind of truth and lie, I think. These people always tell the truth, which is nice. I find it very complicated when people start lying, or when they have the potential to start lying. That opens us up to those kind of statements where somebody says, I am lying, and that doesn't make any sense at all. So that tends to scare me a little bit. Quick shout out to Fake in chat. It's going to be okay. And the best thing you can do is to practice some maths over the summer, which is what you're doing now. Hooray! Okay, let's read out the question, by which I mean, hey Daisy, you read out the question.
Okay.
I'm going to catch up with chat.
So Alice, Bob, and Charlie are well-known expert logicians, and they always tell the truth. So they are sat in a row, as illustrated above. So in each of the scenarios below, their father puts a red or blue hat on each of their heads. Alice can see Bob's and Charlie's hats, but not her own. And then Bob can only see Charlie's hat, and then Charlie can't see any hats because there's no one in front of them. All three of them are aware of the arrangement. And then we've got 5 different scenarios.
Yeah. Quick pause to catch up.
Yeah.
Catch up with the situation. I usually get questions about this, about them being well-known expert logicians. There's a lot of adjectives in there.
Yeah.
And so I think the reason there's so many adjectives there, they have to be logicians because we want them to deduce things. We want to know that they can deduce things, that they're not just randomly saying stuff. They're saying the truth, and they know that they're saying the truth on purpose. I'm not certain why they're declared to be expert logicians. I guess that tells us that they're really good at their jobs. It's nice. Daisy, why is it important that they're well known?
Well known?
It says well known right here.
Yeah.
Can you see? Do you know why it says that?
I could guess. I don't know. But I mean, they are well known now because of the MAT, and also they're just all over any logic course.
Yeah, okay. I guess it's Alice, Bob, and Charlie from the other question. They're famous.
Yes.
There's another reason, which is they have to be known to each other. You can run into trouble if the people in this scenario don't trust each other for some reason. Then so Bob and Charlie can't see all of the hats. They're going to be getting information from Alice, and they have to trust Alice. And the best way to trust someone is if you know that they're an expert logician.
Yeah, but how do you know that? So how does Charlie know who's behind them? Like how How does it?
Wow,
How
so
do they
there's
know
there's
that
there's this part down here. All three of them are aware of this arrangement somehow, right?
Oh,
So,
so
it's been that somebody's added I can sort of see the DNA of it, right? That someone's added these little caveats or bits of extra information to make
and they can
sure that the
and
communication works.
they can discern they can discern Alice's voice from Bob's voice, presumably.
Yeah, and you have to, I guess, assume that all of them. There's some more caveats we might want to put into this. They're going to be either red or blue hats coming around here, and you have to hope that Alice and Bob can see and distinguish red and blue hats.
Yeah,
Slightly awkwardly, I've printed this in black and white on the screen, so you can't tell which hats are which. But that's part of the question, right? To determine which hats are which.
yeah.
Um, so
I think it would be a bit confusing if you coloured them in red and blue.
perhaps if they were coloured in the question for one
Yeah,
example, yeah, don't do that.
yeah,
Yeah. Okay. You said there were about 5 scenarios that we're going to go through. Do you want to? They're all incredibly similar to each other. So do you want to read out scenario 1 and start
yeah.
explaining what's going on in scenario 1?
So their father puts a hat on each of their a hat on each of their hats, and says, "Each of your hats is either red or blue. At least one of you has a red hat." And then Alice then says, "I know the colour of my hat. So which colour is each person's hat? Explain your answer." So if if Alice, so in this case we could, the easier way to consider the examples is to see if Alice has a red hat, could that be possible? And if Alice has a blue hat, could that be possible? So if Alice had a red hat, then if she saw another red hat in front of her, then we wouldn't know. Then they wouldn't be able to know whether their hat was red or not, because they don't have that information. But if they were both blue, then she would know there's at least one red hat, so it must be mine. Whereas if Alice's hat were blue, then at least one of the other hats must be red. So one of Bob and Charlie, or both, have red hats. Then Alice can't tell if their hat is red or blue. So Alice's hat is red.
Nice, I like it. Alice's hat has to be the red one. Otherwise, Alice might
Yeah.
get a bit confused by the red hat that Alice can see. Alice doesn't seem to be confused. Akul in chat asks, "Is the father an expert logician too? Can we trust the father?" Which is great as a caveat, right?
Yeah.
I think I'm not even sure if the father has to be an expert logician so much as just be trusted in that.
Yeah, I think the father would have to be well known and trusted. But like, I think because in the same spirit of things, I would say yes. The father should be he doesn't have to be a well-known expert logician. But then again, neither do Alice, Bob, and Charlie necessarily. Like there are other circumstances where they could trust each other and be telling the truth.
I suppose, yeah. So that, for example, we have to be expert logicians to do this question, but we don't have to be well known in order to do this question.
Yeah.
But maybe, yeah, I think actually in none of the scenarios, nothing that Charlie says ever matters. Like they do talk a little bit sometimes. In some of the scenarios, Charlie gets a turn. Charlie gets to say something. Charlie's my favourite of the three. Sometimes Charlie gets to say something, but nobody ever acts on that information in any of the scenarios. So it kind of doesn't matter that Charlie's famous or whatever. In all of the scenarios, Charlie either doesn't say anything at all, in which case who cares, or Charlie says something and then the scenario immediately ends. So no one had to act on that information. So yeah, okay, we're over-specified.
Also, one thing I'll say is he corrected hats to heads, but I think maybe they were already wearing black hats. and
Yeah, no,
then they
I
had a red, yeah,
I know what I
they had a
did.
red hat put on
it,
top of it.
it should say heads. The thing that's on the
Yeah.
screen is extremely similar to the actual printed question, but is actually not the same thing as the exact printed question. At some point, I've typed up every past question, and I've done it quite
Oh,
sometimes badly. And yeah, if you need a terrible job, then try typing up all of the past questions. See if you can do it
oh
without making any stupid typos.
no,
Oh dear. But it does mean
I
I've
could
written
not.
put a hat on each of their hats, which, yeah, good. It's not the stupidest
Yeah.
typo I made during my project of typing up all of the past math questions.
You could do a lot worse.
You could do a lot worse. Yeah. We can't talk about it on the stream. So, right. Okay. What was the answer then? So the Alice's hat was red, and the other hats are blue. And
Yeah.
I liked the way you worked through it, kind of logically by imagining empathetically as if you were Alice.
Yeah.
What was going on? I guess there's another alternative where you do like a truth table or something, except now it's not
Yeah.
a truth table because everyone's telling the truth. But you just list
Yeah.
the 8 possibilities of what the hats look like. There are
Yeah.
8 because there's 2 times 2 times 2.
Yeah.
Yes, there are 8 3-digit binary numbers. Yes, good. There are 8 possibilities, and just check whether they make sense or not. And this is the only one that makes sense with all the information. Yes, good. Okay. Right. Okay, that was scenario 1.
No.
Yeah. Cool. Scenario 2, new hats, new scenario, new deductions. Let's go.
Yeah. Okay. So their father puts on a new hat on each of their heads and then again says, each of your hats is either red or blue, and each one of you has a red hat. So it's the same sort of scenario as the first question, except this time Alice says, I don't know the colour of my hat. And then Bob also says, I don't know the colour of my hat. Which colour is Charlie's hat? Explain your answer. So I think we can see, similar to the idea of the last question, because Alice doesn't know what hat they have, it must mean that they can see a red hat in front of them. Because we know there must be at least one red hat. So for Alice to not know, there must be there one of them would have to have a red hat. And so if Bob doesn't know if they have a red hat or not, then if Bob could see Charlie had a blue hat, then because Bob would know that Alice has seen a red hat because Bob is an expert magician. So they would then be able to deduce, I must have the red hat because Charlie has the blue hat. So therefore, Charlie would have to have a red hat, because then Bob doesn't know if they've got a red hat or not, and then Alice doesn't know if they've got a red hat or not. So Charlie must have a red hat.
Bob can, so both Alice and Bob can see a red hat. People in chat are making the point that Alice and Bob are not exactly being very helpful. There's nothing to say that they have to be so cryptic, right? Which reminds me of a very good joke about a hot air balloon, which I'm going to do now. Some people are lost in a hot air balloon. They see someone on the ground. They call down, "Hey, we're lost. Where are we?" And the person shouts back up from the ground, "You're in a hot air balloon." To which they say, that must be a logician, because the answer was correct, useless. Alice can't. Alice can see Charlie. Alice can see Bob's hat and Charlie's hat. I know it looks like Bob is in the way, but somehow Alice can see both of the hats. I guess sort of peering around. Yes, I guess that's important that Alice can see both hats. If Alice can only see Bob's hat, then this scenario doesn't make any sense, because Alice would be looking at the back of Bob's head. I don't want to rerun the argument with this different version. I think it's an interesting problem. If they can each only see one hat, I need to not get distracted by that version of the problem.
Yeah.
People in chat. What are the people in chat? I've lost track a little bit of chat. Chat. I like that you're talking to each other. Fake would like to see it one more time. Can we run through it one more time, Daisy?
Um. Yeah. So part
Part
two.
two.
Yeah. Okay. So if Alice doesn't know what hat they have, so she she must be seeing a red hat, because if she saw two blue hats, then she would know I've got the red hat. So Alice sees at least one red hat, and then and Bob can deduce that because Bob's an expert magician. So Bob knows Alice can only see can see at least one red hat. So if Bob saw a blue hat on Charlie, then Bob would know, well, at least one of mine and Charlie's hats is red, so mine must be red. So if Bob is then saying, I don't know, then it would have to be that Charlie's hat is red, and then Alice and Bob have no way of knowing whether their hat is red or blue.
In this case, we've got to really imagine being Bob. Bob's doing a lot of
Yeah.
work in a way. Bob can see Charlie's hat. It's refused to tell us what they can see, and so we don't know. But Bob knows, and they can also hear what Alice just said, and they can themselves as Bob. Bob can imagine what it's like to be Alice. This is second degree empathy, which is just like you're imagining Bob imagining being Alice. So Bob kind of knows what it's like to be Alice, I guess, and to be able to see two hats and still be confused. And Bob gets information from that. I guess the fact that Alice is confused shows us that we're not in part one. In part one, Alice would know the colour of their own hat, but here Alice claims they don't know, not for lack of trying. How many marks do you get if you just write red? I don't know. It does say explain your answer, so I'm worried that you might get no marks. Yes, and people are finding extra holes in the question to make sure that all of the people, as well as being able to see hats, speak the same language, know what red and blue are, have the same concepts of what red and blue mean when you see them. Maybe they've seen some hats before and they're comparing. None of the hats are an ambiguous shade of purple like the live stream.
Yeah.
We can add loads of these caveats, right? I'm wondering if we've got any computer science and philosophy people in chat. Hi, computer science and philosophy people. Cyril wants to know how much you'd write. I would write a few sentences, maybe as many as 3 sentences. Not a paragraph as much, but maybe as many 3 sentences to explain the kind of key points there. I think the key points are something like, why is Alice confused? There's an answer to that question. Why is Alice confused? Why doesn't Alice know what colour Alice's hat is? And then, what does Bob do with that information? And I think probably you pick up at least a couple of marks for explaining in a couple of phrases, maybe only one sentence, what that means to Bob. So I think target here is to write about 3 sentences. I've put an example in the notes. So on the MAT website, there's a solutions doc that's got my attempt at writing a small number of sentences about what's going on. Good, okay. Question doesn't say they can't turn around. You'd think these expert logicians would realise that if they just swiveled, they wouldn't have to make these really embarrassing statements, right? Just pivot. Cool, okay. You can do this version, by the way, with more than 3 people. Someone in chat said inductively, which I want to pick up on. Just like, if they have like 100 people and the front person's wearing a red hat, then everyone else has to admit they're confused. They don't know their hat colour. But eventually all that news, after all of that's been announced, Charlie sitting at the front, here's 99 confused people. They're like, why is everyone so confused about their hats, right? We know there's a red hat. So if you can only, the rules are clear. If you can only see blue hats, What's
I
going
think
on?
that is there's an extension question with something like that.
Yeah. So I added an extension with a billion logicians. If you'd like to think about that
Yes.
version of the problem with a billion logicians, um, please do not do a truth table for 2 to the billion options of what their hats are like. Good. Okay, we've got part 3. I hope people are familiar with the kind of setup now. I'm going to scroll so that these lovely cartoon pictures go off the top, and we're looking at parts 3, 4, and 5 down here. Maybe I can fit the setup, that bit of setup on screen too. There we go. Okay, part 3, new hats. I'll read this one. At least one of you has a red hat, and new information. At least one of you has a blue hat. New hats, new information. Different from the previous part of the question. Alice immediately says, "I know the colour of my hat." Which is pretty astonishing. Alice cannot see their own hat. Bob says, "Mine is red." Well done, Bob. What colour is each person's hat? Well, we know Bob's colour of hat. Bob's got a red hat. Explain your answer. Over to you, Daisy.
Okay.
Do you trust Bob, by the way? I suppose you have to.
Yeah. Well, they're well known. Well, earlier we said that well known implied trusted. So, but I mean, well known people in the real world are not to be trusted.
But expert logicians as well, right? So they're expert logicians.
Yes.
They're telling the truth. I guess. I guess we
Maybe.
trust Bob. I think I
Yeah.
trust Bob. We'll be able to deduce it as well. I think. So
Yes. So
let's go. Okay, over to you.
So if Alice knows the color of their hat, so because at least one of them is red and one of them's blue, then Alice must either be seeing 2 red hats or 2 blue hats, because otherwise, because if they saw 1 red hat and 1 blue hat, then all the conditions would be satisfied, so Alice wouldn't be able to tell. Yeah.
Once you've had the matching hats idea, it really falls apart. So that's the bit. If you're not sure about that, focus on that idea.
Yeah.
Why did Alice must be able to see matching hats?
Yeah, and also Bob can tell then, because Bob knows that Alice can see matching hats. So if Bob sees Charlie with a red hat, then Bob can say, "I've got a red hat." So we know that Bob and Charlie have red hats, and then Alice has a blue hat.
Yep. So I think it goes blue, red, red. But you kind of deduce them in not that order.
Yeah.
I guess you deduce Bob's pretty early on, and Charlie's matches. It's nice in this case, by the way, that Bob actually says something useful.
Yeah.
There's another version of this, I guess, where Alice says, "I know the colour of my hat." Bob says, "I know the colour of my hat." And then they stop talking. And then that's quite nice because 2 of them know the colour of hats, but I don't know.
Yeah.
I guess there's a little bit sad that Charlie doesn't know. Oh no, Charlie knows. What does Charlie know?
Well, Charlie's an expert logician. So in this case, Charlie knows it. I think in these scenarios, Charlie would know it exactly the same as we do.
We're Charlie. We're Charlie.
Yeah.
Charlie can't see any hats like us. Charlie just deduces stuff. We're Charlie. Brilliant. Okay. Can you mention websites you've made in your personal statement? Yeah, why not? Personal statement, right? You can put whatever you want in. Can it not be red, red, blue? If it's red, red, blue, Alice wouldn't know that it was red, red, blue. Here's the thing. If it's red, red, blue, then that matches the condition that their father gave them. Red, red, blue. But Alice wouldn't know that it's red, red, blue because it might be blue, red, blue. And Alice can't tell which of those it is. Both of those work. I guess there's not that many possibilities for what the hats are like. Oh, is it 6 possibilities, I think, for that match the father's condition? 6 possibilities. Before any of them start talking, there are like 6 possibilities. And then as they start talking... No?
Yeah.
Yeah.
Well, it sounds like it should be 6 because it's well, there were 8 in total without any conditions because it's 2 to 3, and then the only ones that wouldn't match are all red and all blue.
Yes, 8 takeaway 2 is 6. Welcome to the MAT livestream.
Yes.
The personal statement is getting changed, but not for the current admission cycle. So it's the same. There's current consultations about what's going on for 2025 admissions, but that's not the round that we're currently in. If you're watching the replay in the future, then hey, what's the future like? And also, what are personal statements like? Let us know in the comments. Now I'm going to have to track the comments on this video. They come back. Right, okay. 2 multiplied by 3 choose 2 is 6 as well. So someone in chat has got a multiplicative way rather than a subtraction way of getting to 6.
Yeah.
Phew. 6 possibilities is not that many. You could check all of them and see if they make sense.
Yeah.
We could be doing case checking.
Yeah.
Do we like case checking?
No, because not as a computer scientist. Because like if we had, say, 1 billion hats, then that would be 2 to the billion cases. It's not very efficient.
This is the thing that my brain can't do. I can't do this kind of like efficiency thing, right? Because I think 2 to the billion, just check the cases, right? See what happens. Right? I know it's a lot. But,
I mean, there are times where we think like that as well, and it can be quite useful. You just go, 2 to the billion, that's good enough.
Okay. Got a computer, right? You get your computer to look at all the 2 to the billion cases. It's not I see what the big problem is. It's not like prime numbers where there's infinitely.
I mean, like a Turing machine can do it, so
right, okay.
That's fine.
I think we had something approximating a Turing machine in Matt one time. Or something that did some sort of. We had some finite automata. It was very. It was one of those questions that involves a lot of reading.
They were a lot of fun.
Maybe we'll get there on the stream one day. Good. Okay. We've got a couple of parts left, and because I have been interrupting a lot, we're slightly behind on time. So I'm going to let Daisy do parts 4 and 5 when you're ready.
Okay. So Father says each of your hats is either red or blue. At least one of you. So it's the same scenario. At least one of them has a red hat. One of them has a blue hat. So Alice says, "I don't know the color of my hat." Bob says, "My hat is red," and then we want to know what Charlie's hat is. So if Alice doesn't know the color of the hat, then it must be the opposite scenario to the previous part. So it must be, so instead of being red, red, or blue, blue, it must either be red, blue, or blue, red. So Alice is seeing either red, blue, or blue, red. So and Bob knows that, because Bob is at least as good as us at logic. So Bob knows that it's either blue, red, or red, blue. But Bob can also see that Charlie's hat is either blue or red. So if Charlie's hat were red, then that'd be a contradiction. So Charlie's hat is blue and it goes red, blue. So Charlie's hat is blue.
Really nice. I think this reminds me a little bit of the first couple of parts of the question, or like part 2, where Alice was a bit confused because they could see non-matching hats, and here it lets us deduce something. So that's kind of quite nice. And then last part, Father gives them some different information in this case.
Yeah. So in this case, the same thing. I like each of your hats is either red or blue, but in this time, 2 of you who are seated adjacently both have red hats, and then Alice doesn't know the color of their hat. So in this case, we could consider both possibilities for Charlie's hat. So if Charlie's hat were blue, then Alice and Bob's hat would both have to be red, because that's the only way you can fit 2 of them being sat adjacently and both being red. So in that case, Alice would know what her hat is, and it would be a contradiction. But if Charlie's hat were red, then we know that Bob's hat would. Well, we know that Bob's hat always has to be red, because if Bob's hat were blue, then there's no way you could get. Alice and Charlie don't sit adjacently, so that's just impossible. So red is the only other. So yeah, so if Alice sees two reds, then it's impossible to deduce whether her hat is red or blue. So Charlie has a red hat.
I think that's the key. It's that although the statement says two of you, it's possible that all of them have got red hats. I guess this would be the father not being very useful this time to saying that two of them have. It's slightly sneaky for the father to say two of you who are seated adjacently both have red hats if all of them are wearing red hats. But I think it is still true that two of them who are sitting adjacently have red hats. They're all sitting there in red hats. Alice says, I don't know what you've done, because nobody knows what my colour hat is. There's all these red hats around. Doesn't mean I've got one as well, though. Yeah, that's the confusing case. I like the way that Bob has correctly deduced that Bob has a red hat twice, and is then rewarded by being given a red hat that everybody knows about straight away. The father gives them this condition which forces Bob to get a red hat. They don't do any talking in this part, they just happily sit there in their red hats. Maybe, I like to imagine it's the same red hat that they were just like, you keep that one. Yeah, cool. So each part I think is worth about 3 marks.
Yeah.
So, yeah, good. Okay. What colour is Charlie's hat? There we go, cool. Well, did you see the other ones? I guess we don't know Alice's hat at the end of that one. Right, good. Okay. We've hit 1 hour. Don't forget to blink if you've been looking at a screen for the last hour. Don't forget to drink water if you haven't consumed water in the last hour. Remember to remain human. And if you've been thinking logically for the last hour, remember to think illogically for just 20 seconds to give your brain a rest. Remember to think illogically is to be human, and you've got to remember that as well as being an expert logician, also a mammal.
Yeah.
I've got this theory that mammals, we're just not that good at logic, really. I've got a kind of evolutionary theory for this, which I won't bore you with now. It's for me to explain why I'm not very good at algorithms.
Yeah.
Good. So important point there that they should be blindfolded when the hats go on. It's not much of a game if they all see the hats going on. Yeah, it's good. People in chat are taking my instruction to think illogically. Good.
Well, you could put the hats on from behind, because we know they don't have the hat.
Yeah, you'd have to walk it. So you give Alice the hat and then but it doesn't matter. You go and give Bob the hat, and Alice sees that, but they're going to see it, I suppose, anyway. So that does check out. I like that as a strategy. Right, cool. We've got some more well-known expert logicians. Maybe it was a mistake to do 3 of these in a year, 3 of these in a row, or Alice, Bob and Charlie to turn up 3 in a row, because once you've done something 3 times in a row, people really expect it as a pattern. And it means for 10 years after this, we've been asked what happened to Alice, Bob and Charlie, right? So maybe that was a mistake to set up a pattern like that. You'll notice we're doing 2 computer science episodes, not 3, because if we did 3, then you'd expect them every week forever. Good, right, okay. We didn't get a blink reminder last week, so Charlie in chat has not blinked for an entire week because I forgot to tell them to.
Oh dear.
Oh no, and we've got now contradictory statements turning up in chat. Oh, chat's really going for this. Wait, Charlie's in chat. And Charlie is actually Herb, but they've renamed themselves Charlie. Charlie's my favourite. Right, good. Okay, it's Alice, Bob and Charlie again. It's MAT 2013. This time, Charlie, my favourite. Charlie's only purpose in this is to write numbers on people and tell them confusing facts. That it's a whale of a time. Let's go. I'll read out the setup and then you can do the scenario. Alice, Bob and Charlie, we just met them, well-known expert logicians, always tell the truth. Charlie's going to write a whole number on each of their Alice and Bob's foreheads. The difference between the 2 numbers is 1, Either Alice's number is one larger than Bob's, or Bob's number is one larger than Alice's. You're going to see that in the scenarios, Charlie also tells Alice and Bob that. So they're not just picking two random numbers, they're picking numbers that are very close together. Each of Alice and Bob can see the number on the other one's forehead, but they can't see their own number because they have eyes in front of their heads facing out of their heads. Right, like normal human eyes. Right. Charlie, right, okay, scenario one. Over to Daisy, scenario one.
Yeah, okay. So Charlie writes a number on each of Alice's and Bob's foreheads and says, each of your numbers is at least one. The difference between your numbers is one. And then Alice says, I know my number. Then we're asked to explain why Alice's number must be 2, and then what Bob number is. So I think here I probably start with what Bob's number is. So, because that's how Alice is deducing what number it is. So, so we know that the number has to be 1 less, or Alice knows that their number is either 1 more or 1 less than Bob's. So it must be that one of those outcomes isn't possible. So the only way that can happen, because there's no upper bound on integers here, but there is a lower bound of 1. So it must be that Bob's is 1, and then Alice can deduce that their number is 2.
And this is going to be relevant later on as well, that if Charlie writes a very extreme number on Bob's head, like for example the number 1 on Bob, I'm not sure what my notation is here. If Charlie writes a very extreme number on Bob's head, then Alice can see that Charlie's pushed things to the limit, and there's now only one possibility for what Alice's number is. Yeah. Okay.
Yeah.
This one-sided number line has only got one extreme, I think is what Daisy's saying. The number 1 is special on the number line.
Yes.
Because it's where counting starts. Oh no.
Yeah.
Oh no. Right, okay. Bob's number is 1. This question, I've noticed how this question has been written in a very friendly way. I think it could say, what is Alice's number? What is Bob's number? But someone's chosen to write it as explain why Alice's number is 2. To contain the number 2 in the question as well. Yeah. Okay.
Yeah.
Charlie.
So,
yeah. Okay.
Although
yeah.
It could Alice's number could be between 2 and 3, not inclusive. Oh wait,
they're whole numbers.
Okay, let's not go there. Okay.
Whole numbers today for this question.
Okay.
Yeah, there's a really good.
Okay.
There's a really good version with real numbers, I think.
Yeah.
Does that work? Yeah. Yes.
Oh,
yeah. Okay. The thing you said is true. Extension question for chat. This one doesn't have an extension question because I couldn't think of anything. Oh no, it does. Oh yeah. Okay. Better extension question. Same thing, but with real numbers. Bigger than or equal to 1. What are the weird things? Daisy just told you, but didn't explain it. So, homework for chat.
I might. Yeah.
So D in chat asks what if Alice's number is 0, and they're all at least. Yeah. Okay. People in chat being very helpful. I like it when chat's helpful. It's good. Right. Okay. New numbers.
Okay. So Charlie now writes new numbers on their foreheads and says each of your numbers is between 1 and 10 inclusive, and the difference between the numbers is 1. Alice's number is a prime, and then it explains that prime number is a number that's greater than 1, divisible only by 1 in itself. And because of this, we know that we're only dealing with integers, whole numbers, which is helpful. So I guess I'd start here by just considering what are the prime numbers between 1 and 10. So what numbers could Alice be? So Alice could be 2, 3, 5, or 7. So if Alice doesn't, so Alice knows that it must be, Alice knows as much as that, at least as much as that. So Alice knows that they must have 2, 3, 5, or 7. So if Alice doesn't know their number, then Bob's must be between two primes, because otherwise Alice could deduce which one it was. Oh dear.
Oh no. Yeah, sometimes the writing makes things go really bad. I was trying to write what can Alice see as like a clue, which
Yeah.
maybe is not a very good clue.
So Alice can see Bob's. So Bob's number must be between two primes.
Yeah, which I think means it's
So
4 or 6.
yeah.
So Alice can see that. If Alice sees 4, then they don't know whether they've got the prime 3 or 5. If they see 6, they don't know whether they've got the prime 5 or 7.
And also we know that Alice's number can't be 2, because then it wouldn't be 1 away from 4 or 6.
Yes. Alice's number. Oh, I see. Yeah, we do know that. That's true.
Yeah.
Yeah. Yeah. I suppose we're getting there. We're going to end up knowing what Alice's number is, and I guess already we can rule out 2 being prime is kind of no longer on the table, because if Alice can see 1, game over, and if Alice can see 3, game over, right? 4's not prime, so it must be 2. Yeah, okay, 2's already out of the frame.
Yeah. And then Bob says that they don't know their number. So if Bob doesn't know the number, so if Bob saw 3, then they can deduce. Bob can deduce at least as much as Alice can. So from what? Bob can deduce at least as much as we can at this point. So Bob knows that their number's either 4 or 6. But if Bob could see that it was 3, then it can't possibly be 6, because that's not 1 more. Or if Bob's number were 7, then no, if Alice's number was 7, then they couldn't possibly be 4. So Alice's number must be 5, because otherwise Bob would be able to tell what their number was.
Yeah, I love that phrase. Otherwise Bob will be able to tell.
Yeah.
This is sort of the only combination. This is the only possibility that's this confusing for them. I guess you could go through checking the other primes and the other cases for the numbers around the prime. So we kind of ruled out 2 already. You could check the other ones and see that in those cases it's still a bit confusing for Alice, because it's still a bit confusing because there are ways it could be confusing, but then afterwards Bob should probably pick up the message from what Alice is saying. We're really relying on Bob being an expert logician. If Bob's just not listening or something, or if Bob's just off doing something else, then Bob saying I don't know my number doesn't contain any information. But because Bob's an expert logician, if they don't know their number, it's because they don't have enough information, that there's some ambiguities.
Right.
And they can see Alice's number. And Bob's got more information than us. They can see the number, and somehow they can't work it out.
So part 3. So Charlie writes new numbers on the foreheads. So now each of their numbers is between 1 and 10 inclusive, and the difference between those numbers is 1. So now Alice firstly says that they don't know their number. So we know that Bob's number isn't 1 or 10, because otherwise we'd be able to tell. And now Alice asks if their number is a square number, and then Charlie says, if I told you that, you would know your number. So it might be helpful now just to consider what the square numbers are. So that's 1, 4, or 9. And we know that Bob's number is such that there is only one square number either side of it. So
I'm going to try and write that on the screen, but keep
Yeah.
talking. There's
Yeah,
only
so-
one square either side of Bob's number. Okay, that's what I'm writing, I think.
yeah. So if there were only one square either side of and there's also exactly one square because otherwise you also wouldn't be able to tell. So there's only an exactly one. It would exactly is a better word than only in that instance.
Using hash.
So in this
yeah, that's right.
Yeah. So in this case, we know that Bob's number is either. So which numbers are next to 149? Well, it could be 2, 3, 5, or 8, and it can't be 10 because we've already ruled it out. So we know that Bob's number is either 2, 3, 5, or 8. But now we know that Bob doesn't know their number.
That's crazy, by the way.
Yes. Yeah. So what are the possibilities? So what are the possible numbers that Bob could see? Well, if Alice had 1, then Bob would know straight away that their number was 2. So we know it can't be 2. So we can rule out 2. If Alice's number were 2, then Bob's number would have to be 3. But Alice's number could also be. So Alice's number can't be 1. So Alice's number can't be 1 or 2.
Yeah. So.
And it can't be 3 because Bob's number can't be 2.
The way I would do this, I think, is to get into Bob's head again. I know Bob says they don't know.
Yes.
But get into Bob's head. Bob's confused, right? Bob knows that the options for Bob's number are 2, 3, 5, and 8.
And we've ruled out 2 now.
Yeah, they can see Alice's number. I think this is pretty similar
Yes.
to what we were talking about before. Is what I want to say. Where we had a confused person who was looking at a number on a forehead, but somehow confused, even though there was some information, right?
So if So if Alice's number were like, so we know that Alice's number can't be 10, for example, or it can't be anything that's not consecutive to 3, 5, or 8. And then, so if Alice's number were 2, then Bob would be able to tell.
Yeah.
If Alice's number were 4, that's a possibility because Bob can't tell.
If Alice's number is 5, then that's actually impossible because nothing on Bob's list is next to 5.
If Alice's number were 6, then it would have to be 5. If it was 7, then it would have to be 8. Yeah, I think it has to be 4.
So it turns out, I think that the only thing that makes sense is for Alice's number to be 4. Is the only thing that's next to 2 of those. The thing, I guess, the way this is similar to the previous part is before there was some restriction on Alice's number, and Bob could see it, but Bob was still confused.
Yeah.
So that meant that the possibilities, it had to be the case that Bob's number could be one more or one less. No. Right, never mind. Okay, I've confused myself by trying to compare both versions of the question at the same time. Chat are also saying things, but because of stream lag, I don't know what's going on. We don't know. Yeah, so we don't know if Alice's number is a perfect square. We do at the end because we know it's 4, but to be clear, we don't know it's a square number midway through. We're just told it was a good question. Alice is asking if it's a good question or not. So let's, just to demonstrate what might be going on, I'm going to show you one example that works. I'm not claiming this is the only example that works, but this is my little puppet show using Alice has got the number in my puppet show 4 written on their head, and Bob has got the number 5 written on their head. This is just one example. In this case, Alice looks at the 5 and says, well, I don't know, it could be 4 or 6, right? Like all I know in this case, the numbers difference between those is, well, I don't know my number. And so they say, I don't know my number. Okay. Then they ask Charlie, is my number a square number? Because they're considering 4 and 6 as the possibilities. So that's a good question if you're trying to decide between 4 and 6. Charlie says, hey, it's a good question. Which Alice hates because Alice knew it was a good question. Alice was asking it because it's a good question, I suppose. Alice could be asking a stupid question, so it's nice of Charlie to confirm that it was a good question. We know these logicians, sometimes they ask questions they already know the answer. Anyway, never mind. Alice has asked a good question, and Charlie has refused to answer it, but has said, hey, what's going on there? Bob is staring at the 4 on Alice's head thinking, well, that is a square number. So mine could be 3 or 5, Bob's thinking. Mine's 3 or 5, and either way, that would have been a good question, because if my number's 3, Alice would be considering 4 and 2, and if my number's 5, Alice would be considering 4 and 6. You see, Bob is imagining what it's like to be Alice. I'm trying to imagine what it's like being Bob, who is trying to imagine what it's like being Alice. It's double depth empathy again. Bob says, yeah, I don't know, because there's 2 possibilities still. It could be that Bob's considering this weird, going to numbers like 3 and 6, but Bob's considering 2 possibilities as well. It turns out this is the only combination where that level of confusion persists for that long. For any other pair of numbers, it turns out they can deduce it much faster, and they wouldn't be this confused for this long. My A's and 4's do look identical, don't they? It's because my A is very 4-like and my 4 has come up very A-like. Okay, let's see if I can fix that. I think I'm making it worse. There we go, cool. At least the 5 doesn't look like a B, right? How could I do my 5 like that, right? I do the 5 terribly, and it could look like a B. Okay, good. Yeah, 5 is between 4 and 6. Yeah. 5 is between 4 and 6. 4 is between 3 and 5. That's kind of the link between the parts. Up here we have this 4-6 kind of dichotomy, and then that gave us 5. Down here 3 and 5 for B. That kind of dichotomy gave us this 4 over here, with some extra confusion around the sides. Good. Okay. Is doing CS questions useful for question 5 preparation? Yeah, I think these sort of questions are just good for you. People who have seen the stream before know that I take quite a wide view about what's useful for maths. I think that it's useful to do past math questions, but you don't have to just do past math questions. I think anything that you find difficult or anything you get stuck on is helpful practice for all of the math questions.
Yeah.
I don't know. Daisy, have you got any recommendations of hard maths for people to get stuck on?
Oh, I mean, I would say step the foundation mod, especially if you start with the foundation modules and then go into step papers. But I know that if you send people there into step,
they don't come back. It's weird.
Yeah.
Sometimes people ask me for more maths, and whenever I've said there's these step foundation modules and step other support modules, nobody's ever asked me a follow-up question after that of can I have some more afterwards. It seems to be a lifetime supply of maths.
Also with the maths, when I did always try and also go through like the questions I didn't do. So when I sat it, I didn't do questions 3 and 4 because there was a. But I think now they're getting rid of question 7.
Back in your day, you didn't do questions 3 and 4, but you're saying you looked at them anyway.
Yeah.
Which is probably good for you. And actually, this year the news is awkward pause while I was distracted by chat. This year, computer scientists are doing question 3. Maybe you'd have liked doing question 3. I don't know. We'll find out.
No.
No? Oh, okay.
I would not have liked it.
That, ladies and gentlemen, and everyone, is evidence that we don't script the party line before going on the show. Thanks, Daisy. Okay, new game. Alice is going to give numbers to Sam and Pam. This time, they're aware of their own number. They're not aware of the other person's number. So, unlike the hats, where they can see each other's hats, and unlike the foreheads, where they can't see their own foreheads, the numbers get whispered to these people in this case. And there's an important caveat. These numbers are going to be X and Y, whole numbers, integers I suppose. Y is bigger than or equal to X, X is bigger than or equal to 1. And Alice is going to tell the sum to Sam, S for sum, and the product, P, to Pam. Those are secrets, but these are well-known expert logicians. There are quite a few scenarios. I think we've got time to work through them. There are about 5 of these. And each one will give some information. Alice, it looks like Alice has found new friends, says Synonymous in chat, which is sad, right? What's happened to Bob and Charlie? Where have they gone? We know they're siblings from 20... The Hats, right? They have the father.
Yeah.
So we know they're siblings.
Although Sam and Pam are not... they're not well-known expert logicians this time.
No, they are. They're sorry, down here. I didn't read it out, but they are.
Oh, I can't read. Oh no,
that's all right.
That's my mistake. But Alice is. This could be a different Alice.
It could be, couldn't it? I haven't been told that Alice is a well-known logician. I guess I just need Alice to be able to add and multiply. Yeah, Alice doesn't give them any other facts through here.
Yeah.
So I separately know that Alice is a well-known logician because, well, Alice is well-known, therefore I've heard of Alice already, which means I don't need to be told.
Yeah.
No, right, moving on.
Okay.
Alice has actually got some friends, which is nice. Okay, over to Daisy for part 1.
Okay, so in the first game, Pam says, "I know the values of X and Y." So what can we deduce about those values, and then explain the answer. So if Pam knows what X and Y are, then there must be so Pam knows the product. So there's P for product, Pam. So there must only be one way of one possible solution which satisfies the requirements. So because we know that X is less than Y, we know that X must be equal to 1, and then Y is equal to the product. That's always a solution. So it must be that X is equal to 1, and then because there aren't any other solutions, we know that Y doesn't have any divisors and is prime. So Y is prime.
And it's nice that we've got a word for these. Numbers, the prime numbers. I don't think you need to say prime to get the credit here. Just something where that's the only possibility. Yeah. That's always a possibility that Alice, being sneaky, might actually pick the number 1 for X. I guess it doesn't have to be prime because X and Y could both be 1.
Yeah.
The answer I've written up on the website is wrong because the answer I've written up on the website says they have to be prime, and it's this extra possibility. Cool. Yeah. Okay. So, it's nice we have this word prime or 1.
Yeah.
Good. Okay.
Okay. So in the second game, Pam doesn't know what X and Y are, and then Sam, knowing that Pam doesn't know, says, "I know X and Y." So Sam is given the sum 4. What are X and Y? So if Pam doesn't know what X and Y are, then we know that the product is not a prime. So the product's not prime. And if the sum is 4, then from what we can tell from the sum being 4, the way we can do that is we could either have 2 and 2 or 1 and 3. So if we had 1 and 3, then the product would be prime. So he knows that X and Y must be 2 and 2.
Nice. There's not very many possibilities if you know the sum is 4.
Yeah.
It's all slightly odd reading this question. Like, oh, it's really mysterious what's going on. It's like these ones where you don't hear anything of the information, and then you're told the sum is 4.
Yeah.
Which is a bit like the ones where Bob says my hat is red. It's just, oh well, sorry, I thought you were extra cryptic, but no, here you are.
I think like in this case, it's like we don't actually need to know that Sam knows what X and Y is because we're given the sum, so we know that Sam knows because we know what Sam's sum is.
Yeah.
So it's almost like too much that we're given.
This is almost redundant. You can delete. Yeah. Okay. Daisy's saying harder question. Look, it's not just me who makes questions harder. Daisy's saying you can delete this line. Yeah. Is it harder or easier?
I think that does make it kind of harder because you're looking at that thinking, what can we deduce from that? And the answer's nothing. Like it's kind of given in like a weird order, this, because we're given the sum right at the end, and it's like,
which is like, we're not Sam. If we were Sam, we'd have found out that information earlier, but somehow we're being told later on in the sequence. I like the way that if Sam says it out loud, now Pam knows, which is nice. I would not ask that. That's not part of the question, but it's just kind of nice that now it's out there.
That Pam knows that, but Pam doesn't know the sum, so you
can't.
Oh
yeah, no, yeah, okay, true.
Yeah.
Sorry, this is one where we know more than
Pam.
We know more than Pam because we know the sum.
Yes. Yeah.
Am I Sam now? I thought I was Charlie before. No, I think we're Sam in this one. We're about to be Pam, aren't we? Because we're going to know the product is 4.
Yeah.
It's weird having information. I'm not sure I like it. I like having no information and being clueless.
Yes.
Having to derive this sort of thing. But I guess there's just too many numbers.
Okay. So, in the third game, the product is 4, and then Pam initially doesn't know what X and Y are, which he already knew because 4 is not a prime. So that's redundant. Sam then says, I don't know what X and Y are. And then Pam says, I now know X and Y. So we can consider here the 2 possibilities for the products. So it could either be, so initially it could either be X is equal to 1 and Y is equal to 4, or it could be X is 2 and Y is 2. So those are the 2 possibilities. So if for example the sum was 4, so X is equal to 2 and Y is equal to 2, then Sam would get 4, and then because the sum is 4 from the previous part, if Pam knew the sum, then it would be so if the sum is 4, then
we now know that this line at the top is sort of code that, well, it's not really code, but this just means that that product is not prime.
Yeah. So we've got either, so the 2 possibilities we have is that So we could have x is 2 and then y is 2, in which case the product for Sam would be 4.
Yeah, the
And
sum for Sam
the
would
sum,
be 4.
so Sam gets 4.
Yeah, okay.
So
then,
and then but then in that case, from the from the previous part, we can kind of use that again, and we know that then based on what Pam says, Sam knows what.
yeah.
So we know from that.
Oh, that's
So
sneaky. I like that.
Yeah.
Oh, I see. You're trying to leverage. You're trying to use part 2.
Yeah.
So we could rerun some of the argument that we just did for part 2, but you're using the
Yeah.
result, which is to say something's different now. The sum's not 4. Otherwise, Sam would, like in part 2, immediately deduce it. That reminds me of the hats. Actually, there was a bit in the hats where first part Alice knew what was going on. Second part Alice is now confused. So something's different. That happened a couple of times. Here it's like, if the sum's 4, then we've seen that Sam is very confident and deduces X and Y. Sam's now confused, so the sum's not 4. I quite like that as a way of like building off what we just did. Okay.
Yeah.
I can't write.
So
writing is not good.
Yeah.
Go.
So
okay.
the other possibility is just X is equal to 1, and then Y is equal to 4.
And it's quite nice that there's only 2 possibilities. A while ago we were talking about 2 to the billion of possibilities for having a lot of people wearing a lot of hats, but just having just 2 to the power of 1 possibilities is just it's quite nice. Worst case scenario, you can just sort of check both and see if they make sense.
Yeah.
Cool. Though that said, I fear that by the next part, product is 8. It makes me think 3 cases, but we'll see.
Yeah.
See when we get there. How are we doing? Can't be 2 and 2. So a cool in chat says can't be 2 and 2, as we would be in the situation of part 2, and Sam would know. Yep, there we go. There's exactly the thing going on. And we're talking about map marking in chat as well, but I'm not going to read it out. If you would like to know about map marking, I can't put chat on the screen today. You can ask me in the comments or send us an email at the address on the YouTube description. Or tune in another week and see if chat's working that week. Cool, right, I'm going to type a response in chat. We've got a 4th game that involves the number 8. Which I think just means more possibilities. Bigger number, bigger problems.
Okay.
Unless it's prime.
So Pam says, I don't know what X and Y are. Then Sam says, I already knew that. And then Pam now says, I know X and Y. So we know the product is 8. So Sam knows that Pam doesn't know what X and Y is. So let's think about this. So Pam would know what X and Y are when the product is prime. So if the product is prime, then we have X is equal to 1 and then Y is equal to a prime number. So we know that the sum cannot be 1 more than a prime, because if that were the case, then it's possible that that Pam would know what X and Y are. So that rules. So if we consider the possible product, the possible ways we could do 8, we could have 1 and 8, we could have 4 and 2, or we could have 2 and 2. However, we could have 1 and 8 or 2 and 4.
Time to factorise 8, gang. Right, yeah, so like 1, 8. This is where I have to remember that the factors are in order as well. So it's not that bad. Is it 3 cases? There's only 2 cases.
There's only 2.
I confused you.
Yeah. Well, so it'd be 2, 2 and 2. But yeah, but if it were 1 and 8, then
yeah, what was I thinking for my third way to factorise 8?
Yeah.
I'm really sorry, Daisy.
Well,
this is much worse than the time I accused you of breaking a vase.
If we were factorising it into like any any number of things, then it would be 3. I think. I hope.
For some reason, I'm not counting 8, comma 1. So
Oh,
Hmm.
well,
Don't
I
try and
think.
explain. Don't try and explain my
Okay,
mistake. If
right.
if you're trying to get into
Okay.
my head, I'm not an expert
Yes.
logician, so it's going to be very very
Okay.
terrible.
Okay.
Um,
So if so, Sam knows that Pam. So the cases where Pam knows is that Pam has a prime number. So than the sum can't be one more than a prime. Otherwise, that would be a possibility, and then Sam wouldn't know that Pam doesn't have prime. So in the case x equals 1, y equals 8, that's 1 more than 8, so that could work. But in the case x equals 2 and y equals 4, Sam doesn't know, because Sam would then get the number 6. So Sam wouldn't know that it wasn't 1 and 5, which would make it a prime, and then Pam would know. So it would have to be x equals 1 and y equals 8.
check the 2 possibilities, eliminate one of them, and you're fine.
Yeah. Yeah.
Gosh, counting is tricky.
Yeah.
Good. Okay. Is the sum right? Tell me the sum's got more cases, right? The sum's got more cases? No, it's 2 cases again, isn't it? The sum is 5. So I'm skimming down,
Yeah.
and now I've learned that the information's at the bottom, right? The sum is 5. That's either 1 plus 4,
Yeah.
or it's 2. Wow, that's terrible. Or 2 plus 3.
Yeah.
So it's just 2 cases again.
So I think maybe we could try both and see what happens.
Yeah. Do you want to try talking through one of them?
Yeah.
Or both
Okay.
of
So
them?
let's say we have 1 plus 4. So in that case, Pam gets 4. And so the first case is Pam doesn't know what x and y are, which is true because 4's not prime. So it works so far. And so Sam doesn't know what x and y are, which is still true, because if Pam had said 2 and 3, so if the product had been 6, then Pam wouldn't know either way. So this is getting quite confusing. So far, at least in the case 1 plus 4, Sam doesn't know what x and y are. And so Pam has a product 4 and doesn't know what x and y are. So if so Pam's product is 4. So we know that the sum could either be 1 and 3. So no. So from Pam's perspective, it could either be 1 and 4 or 2 and 2.
Yeah. Pam's got to worry about 2 and
2.
2,
So
which
2
also
and 2 and
multiplies to
2.
4.
Yes. So
I'm going to try and write that down. Wish
yeah.
me luck. You can keep talking, but I'm going to try and write down Pam's thinking. So we're in the case first, this 1 plus 4 kind of world,
Yes.
which I'm going to write at the top so that we remember that that's what we're doing. In the
Yes.
1 plus 4 world, here's what's going through their minds. Pam would get 4 for the product, and then Pam would be thinking about the 2-2 case as
Yes.
well as the 1-4 case. That's Pam thinking.
Yes. So
Pam doesn't know.
yeah. So it could be that. So if it's in the 1 and 4 case, then so far everything's been consistent. if it were in the 2 and 2 case, then Sam would have the sum 4, and if and then if Pam doesn't know, if the sum was 4, then Pam not knowing X and Y would mean...
Oh, chat's come to our rescue. We've got slightly lost, but it's okay. Chat's come to our rescue. Chat says that if the sum was 4, we did that one way back at the top.
Okay.
They're using part 2 again. Chat wants to use part 2 again. So Pam's considering this case. This is Pam at the start, considering, okay, maybe I've been given the product for either it's 2-2 and 1-4. If it's 2-2, then at least Sam will be able to work out what's going on.
Yeah.
Because that's precisely what's going on in case 2.
So let's go back down.
Right.
Okay.
So way up here it turned out to be 2-2. This was the 2-2 case all the way up here.
Yeah.
But now Sam is confused.
Yeah. So the 2-2 case doesn't really work.
So Pam's no longer considering that, I guess. That says I don't know what X and Y are. I've become worried that my web solution is wrong. I'm reading along on a web solution that I wrote up.
Yeah.
I'm now worried. We know the sum's 5.
Yeah.
Yeah.
So Pam would then surely be able to deduce that X is equal to 1 and Y is equal to 4, because from the first part, Sam would then know.
Okay. Do we have to think about the 2 plus 3 world separately? Should we give that a go instead?
Yeah, I'll give that a go. Yeah.
Let's give that a go. So in the 2 plus 3 world, totally separate. The product would be 6.
So that works because Pam doesn't know what X and Y are.
Sure. It could be 1 and 6, or it could be 2 and 3.
And then
I guess I have to write that down.
And then Sam doesn't know because we already know in the 1 and 4 case that Pam doesn't know either. So that works so far.
I'm worried that the 1 and 4 case is what we did in part 3, right? Where Pam deduced X and Y in the next step.
Yeah.
There. So I guess Pam's ruled out the 1 and 4 case now.
Yeah. Yeah. Suppose. Well, but if we want 2 and 3, then the product's 6. So the other case would be 1 and we're only on the second line here. So the other case would be 1 and 6.
Yeah.
So we're okay at the second line. So the first 2 I think we're fine with so far.
Okay.
But now we're on Pam saying I don't. So we're on the third line. Okay.
With you.
So Pam doesn't know what X and Y are. So in Pam's mind, the sum could be 2 and 3, which we've considered. That works out fine. Or it could be 1 and 6. So if it were 1 and 6, then the first line still works. Pam wouldn't be able to tell. So Sam wouldn't know what X and Y are because it's not one more than a prime. So Sam can't tell. Because we've done that I think we did that in a previous part. Is that if Pam doesn't know what X and Y are, then the only thing we could deduce is that it's not a prime. Is that we've not got a prime product. So and because 1 plus 6 is not 1 more than a prime, that wouldn't tell you anything really about X and Y, would it? Yeah, in the 1 and 6 case, yeah, we wouldn't. No, yeah, because we could do 1, yeah. So that works. So I think in the 1 and 6 case, those statements both hold.
Yep.
So I think the 2 plus 3 case works so far. And so Sam now says, I now know X and Y. And so the 2 possibilities were 2 plus 3 and 1 plus 4. Sam knows are the same that we do. So if it were 1 plus 4, as we say, it would have been a contradiction. But we know that 2 plus 3 has no contradiction. Therefore, X is equal to 2 and Y is equal to 3, I think. Because when Sam says, I now know X and Y, Sam doesn't know anything that we don't.
I'm with you.
Yeah.
And yeah, I'm with you. The reason I'm looking shifty is that a couple of days ago I put a solution on the website, on the MAT Livestream website, and it's complete nonsense. The thing I've put on the web is just wrong. And that's why I get an actual computer scientist on to do computer science episodes.
Yeah.
Thank you very much, Daisy. Oh my goodness. I hope nobody looks at my web solution because it's possibly the most incorrect thing I've ever put on the internet. Please don't prove me wrong. The most incorrect thing I've put on the internet.
Most incorrect.
Most incorrect? I mean, it proudly concludes that the numbers are 1 and 4, so I've gone totally wrong.
Oh yeah,
somewhere in the middle.
the conclusion's wrong.
Yeah. Yeah, totally wrong. Everyone's already seen it, so it's terrible.
Yeah.
At least this is the stupidest thing I've done on the internet so far.
Well, I mean, I hope I haven't got it wrong.
No,
both got.
I've sneakily checked the sort of official solution from 2014 while you were talking, and
Okay.
I agree.
All right.
I can't go through. The chat wants to go through it again. Don't make me go through it again. Chat summary here. There are only 2 possibilities for what the numbers are. I'm going to do the quick version. There are only two possibilities for what the numbers are. If you really concentrate and do a kind of nested empathy thing where you imagine Sam imagining being Pam, imagining being Sam again, then one of the possibilities doesn't make sense. Don't ask me which one it is. Daisy's just done something on the MAT Livestream to talk about it. And that video is going to be there to rewind it. Nobody should look at my solution on the website. If you're watching the replay over the weekend, hey, I already fixed it in the future. So that's how time travel works. Good stuff. Are you allowed to use previous parts in your answers? Yes, you're allowed to use the previous things. Cool. Okay, on that kind of calamity for me, but total success for Daisy, I think we say thank you very much for coming on the live stream, Daisy. Thanks for being back on the show. Really quickly, if anybody wants to ask questions, provided the question is not why is James so bad at this? People are now questioning, people are now asking tricky questions like, am I ever wrong in a professional context, and would I like to do any, have I ever made a sort of mistake resulting in accidental, okay. I'm now being accused of other crimes, of course, so that's what chat's like. Daisy, it's been a delight having you on the show. Thanks for getting the answers right, which and way more than that as well. Dresden chat wants to draw a decision tree, which I sort of think is what I'm going to do after the live stream in order to fix the thing that I've incorrectly put on the internet. Decision trees. Been a while. Good, right, next week, more computer science. with another computer science guest. Don't worry, another computer science guest to do some more questions. Chosen this time from question sevens from previous math papers for next week. We'll have a look at some other computer science questions. Thank you once again to Daisy. Thanks to everyone for watching. And we'll see you in 166 hours for another episode of the MAT Livestream. Take care. Bye.
Yeah.
And then I press this button to turn it off.